Education Corner. Yesterday we have completed in our first chapter Theorem 1.1, that is Euclid's division lemma. Let's recall once time. Given positive integers a and b, there exists unique pair of integers q and r satisfying a is equals to bq plus r, where r is greater than 0 or equals to 0 and less than b. And we also saw that how to solve problems based on Euclid's division lemma and how to find HCF with the help of Euclid's division lemma. Now we are going to solve exercise 1.1. This is our exercise 1.1. Now we are going to solve the problem. See here, our first question is to find, using Euclid's division algorithm, to find HCF of, we have here 3 questions. We have to find HCF of these 3 cases. Okay. So the first one, 900 and 270. Here the big number is 900. So we can take A as 900. First, what is the Euclid's division lemma? It is A is equals to BQ plus R. Okay. So we can take A as 900 is equals to BQ plus R. These 270 into, what's the Q? Into division, you get the answer easily, that is 270 into 3. I write 3 because if I write 270 into 4, it gives the value more than 900. So I am writing 3. 270 into 3. 273 is 81. So remaining 900 minus 81 is 90. Okay. Now take A is equals to 270 is equals to 90 into 90 is 27. So 93 will be 270. Plus, so 93 is 270, then there is no remainder, so it becomes 0. Therefore, the HCF of the both numbers 900 and 270 is equals to 90. What the value we got here should take as HCF. Okay, now let's go on to the second problem. 196 and 38220. So we are going to find HCF of 196, 28220. By doing division we can get, so first take A as 38220. You can do division 38220 by 196, or you can do in the form of division method. If we do, we can get 196 as B into 195. 196 into 195 is equals to 38220. I got this value by doing division. You can also do division. So the remainder will be 0. Therefore, the HCF of 196 and 38220 is equals to 196 because of these values given us HCF. Now let's go into the third problem. That is 1651, means 1651 and 2032. Now this is the bigger value. So take A as 2032 is equals to B as 1651 into, if we do division we can get, or if we not do division also we can get very easily. 1000 is 2000 and here it becomes 12. But here it is 0. So we can take as 1. So 1 plus 2032 minus 1651 is equals to 381. Now take it as A 1651 is equals to 381 into 381 5s are 5 3 15. Right, 8 becomes 16. So it is greater value than this. So I am taking 4. 4 is equal value. So now if you take 381 4s plus 127 will become remainder. And again take 381 as A is equals to 127 as B into 127. 3 times will be 381. So remainder will become 0. Now here the HCF of these two numbers will become 127. See how we find HCF? Now let's go into the second question. Use Euclid's division lemma to show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. See here what they asked. You have to show that any positive odd integer will be in the form of 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. Okay, to find this solution, first we have to know they asked to find us using Euclid's division lemma. So I am taking Euclid's division lemma. It is A is equals to BQ plus R. First you write A is equals to BQ plus R. What is this? Euclid's division lemma. Okay, you have to put the bracket. So this is Euclid's division lemma. Then what is the value of A, B and R? We have to find, right? So first here A is equals to, they asked us to show any positive odd integer. But we know that 2n, if it is in the form of a number, is in the form of 2n, then a number should be known as even. If it is in the form of 2n plus 1, then the number is known as odd. Okay? If it is 2n, it is even. If it is 2n plus 1, it is odd. We know that. So we don't know, we can't take even number or else odd number. So we are taking only positive integer. It may be even or odd. So we are taking A as any positive integer. A as any positive integer. Now let's go into the B. Here we can know the value of B is 6, right, in all the cases. So B is equals to 6. Now Q is some integer, where Q is some integer, so leave the Q. And R is equals to, we already know that R and less than B. So what is the B here? It is 6. So we should take R as 0. 1, 2, 3, 4, 5. We can't take R as 6 or greater than 6. So we got all the values. Now let's substitute this value in some equations. So first I am taking R is equals to 0. In the first case I am taking R is equals to 0. So what should I take? A is equals to BQ plus R, where A is equals to some positive integer. A is equals to 6, Q is some Q and R is equals to 0. Okay. So now A is equals to 6Q, right? And 6Q can here 6q is even number. Okay. Now let's go into next sum. Next step, that is r is equals to 2. Now we are taking this many off because we got 0, 1, 2, 3, 4 and 5. So we are doing all this. A is equals to b q plus r, where r is equals to 2. 6q plus 2. Now let's check. 6q plus 2 is even or odd. We can write 6 as 2 into 3q and 2 ones are 2, right? Plus 1. 6 3 is 3 2 6, 2 ones 2. Okay. So now here we can write let 3q plus 1 is equals to n. Let 3q plus 1 is equals to n. Therefore a is equals to 2. The whole value will become n. So this number is even. Okay. Now let's go into the next one. Here now r is equals to 3. A is equals to bq plus r, where a is equals to 6q plus. Now we are taking r as 3. So a is equals to, what we can do? We can write this 3 as 6q plus 2 plus 1. Okay. 2 plus 1 is 3. So a is equals to, now take 2 as common. 2 3 is 6q plus 2 table 2 1s are 2. Okay. Now this one will be left as aside. Now we should take 3q plus 1 as n. So write 3q plus 1 as n plus 1. So it is in the form of 2n plus 1. So the number is odd. Now r is equals to 4. Okay. A is equals to bq plus r. Here a is equals to 6q plus 4. A is equals to 6q plus 4 only. Here we can take 2 common, that is 3q plus, now 2 table where the 4 it is 2 2s are 4. Right. So let 3q plus 2 is equals to n. Therefore a is equals to 2. Whole value will become n. So 2n. It is in the form of even, right? 2n is even. Now we have the last one, that is r is equals to 5. A is equals to bq plus r and a is equals to 6q plus 5. A is equals to, now write 6q plus 4 plus 1. Okay. 5 as 4 plus 1. Now what will become again? 2 as common. 2 3 6. 6q plus 2 2s 4. 1 will left over. So let 3q plus 2 is equals to n. So take 3q plus 2 as 1. Sorry, n. Then a becomes 2. The whole value will become n plus 1. Okay. So it is in the form of 2n plus 1. Right. Therefore we can say it is an odd number. Now let's check. It is odd. First one, that is of 6q plus 1. Yes, in the question we got it correct. And next we get the odd number is 6q plus 3. Yes, it's also correct. Now we got the odd number as 6q plus 5. In the question 6q plus 5. So lastly we should write conclusion that therefore any positive that is odd integer, okay, any positive odd integer is in the form of, either you can see and write this one, or by seeing question also you can write in the form of 6q plus 1, comma 6q plus 3 and 6q plus 5. So this is second question. If they ask to show us any positive even integer, then we should do same like this, but we have to take here positive even integer and here 6q plus 0, 6q plus 2, 6q plus 4. It will become then any positive odd, even integer. But in this question they asked odd integer, so I take only odd values. Okay. Now let's go into the second question. Second question is use Euclid's division lemma to show that the square of any positive integer is in the form of 3p plus 1. Okay. Now what they asked? To show the square of any positive integer in the form of 3p or 3p plus 1. Now take a is equals to pq plus r. This is known as equals to 3 into 3q square. Okay, now let in the bracket what we have 3q square. Now let 3q square is equals to p. Okay, why I am taking p? Because to show in the form of 3p. So a is equals to, for 3q plus square is equals to p. Therefore a square is equals to 3 into, instead of 3q square I am writing p. Yes, we showed that any positive integer square in the form of 3p, and we also supposed to show 3p plus 1. So we are going to do that now. See, take the equation a is equals to q plus r. Now take 3q plus r value as 1. Okay. Now see here, square on both sides. What we get when we do square on both sides? We get a square is equals to 3q plus 1 whole square. Now apply the formula a plus b whole square. That is a square plus b square plus 2a. If you want, we can write that formula. What the formula I used is a plus b whole equals to a square plus b square plus 2ab. Okay. Now take value of a as, a square is equals to, take common 3. Here we have 3 into 3 because it is 3 square, right? So 3 into 3. That is of 3q square. Okay. Plus 1 square is 1 plus same I am writing 3q into 1 will be 3q. So 2 into 3q. Now I am taking 3 as common. So this 3q square. And if you see here, I am leaving 1 because it can't take as common. But if you see here, I am taking 2q and the 3 I am keeping out plus 1. Now take here, let the value in the bracket 3q square plus 2q is equals to, take as p. Okay. A square is equals to 3p plus 1. So any positive integer square is equals to 3p plus 1. So we showed as 3p and 3p plus 1. But we have r as 0, 1 and also 2. We showed to 0 and r as 1. But we have to show r is equals to 2 also. Now let's show r is equals to 2. That is a is equals to same 3q plus 2. Now we are going to squaring on both sides. We get a square is equals to 3q plus 2 square. That is a square is equals to 3q whole a square plus 2ab plus b square. Okay. Now see here, take 3 as common in all. Here 3 if we take common it becomes 3q square. Here it is 3q whole square but here it is 3q square. See the difference. Plus I am taking 3 out so it becomes 2 to 4q. Okay. Here 3 plus 1. I am taking 2 to 4, right? 2 to 4 I am taking as 3 plus 1. Now let's take only for these common. Now again write in another step
3q square plus 4q, this 3 here, plus 1, plus 1. Okay, why I am writing, if you see 3, 3, 9, so it becomes 3q square, 9q square, 3 4s 12. If you see here also 3 2 6, 6 2s 12. Okay, and it is 4. I make it as 3 plus 1, and 3 plus 1 is 4, right? 3 1s are 3 plus 1 4. So I take common like this. Let 3q square plus 4q plus 1 is equals to p. Okay, so what will become is a square is equals to 3. We are taking whole bracket value as p plus 1. So finally what we done here, therefore every square of any positive integer is in the form of 3p and or we can keep or we can keep comma 3p plus 1. Okay, see friends, we have completed first problem, second problem and third problem in exercise 1.1. We have completed these 3 problems. In the next video I am going to do 4th problem and 5th problem. Thanks for watching. Please subscribe our channel.